Hi, this presentation was developed for the Control and Sensing Systems unit of the Combined Electronics Framework at Bournemouth University. It's the third part of the section on stochastic processes in a sequence of short videos to support the unit studies in robotics, and in particular the work on Kalman filters. It follows on from the second clip, which looked at the relationship between stochastic signals and probability distributions, particularly the Gaussian distribution used in the Kalman filter. This clip introduces measures of stochastic processes with an emphasis on variance as a measure of signal intensity. Now we can divide measures of stochastic signals into the amplitude and time frequency dimensions. In this clip, we'll concentrate on measures of signal amplitude and their derivation from both signals and probability distributions. In short, variance is a convenient measure of signal intensity, as illustrated here for zero mean signals with variances 1 and 10. Now our objective is real-time data filtering, rather than say smoothing or prediction operations. And in this case, the processor receives a stream of sample inputs. It doesn't have the luxury of being able to access the whole range of the signal. All it has are those sample values received up to the current time instant. The best guess the processor has then for any statistical measure of the signal is a so-called expected value, based on this received information and represented as a big E with curly brackets. For example, the expected value, or best guess of what the next sample is before it arrives, is a simple average of all the k samples received up to that point. We'll use expectation as synonymous to the mean or average value, indicated as a flat hat over the x here. We'll also be using expectations of the square of the signal and other statistical measures defined in the same way as our best guess or average of the measure based on the data samples received up to the current time instant. It's straightforward to find the mean from sample values of the signal, but stochastic signal values are modeled by a probability distribution, and it's also possible to derive statistical measures from this as well as from the signals themselves, as we'll see in this section. Let's go back to the fair and uniform rolling die to check this out. The probability p of throwing any number is p equals 1 upon 6. If we throw the die n equals 600 times, say, then we can expect to get p times n of any number, that is, 1 over 6 times 600, or 100 ones, as well as 100 twos, 100 threes, and so on. We can then count up the score achieved by each number as the number of times it comes up, Pn, times the face value x, so that the score in 2s, say, is Pn times x equals 2, or 200. The score in 3s is 300, and so on. Now the average score we get in our 600 throws is going to be the total score found from the sum of our 6 Pnx scores for each number, divided by the 600 throws. Since n is in every term here, we can cancel it out to get the formula for mean in terms of probabilities as p times x summed over all 6 possible values of x. And if we apply the formula back to the die, we find that our 600 throws gives us an average value of 3.5 for one throw. And then if the average score when throwing a fair die is 3.5, you might expect to score that when you throw a die. You might also be quite surprised to score 3.5 on one throw of a fair dice, which is perhaps a good point at which to mention the myriad gotchas in this topic, and to note the warning so eloquently stated by Mark Twain here. Bearing this in mind, we'll bravely take our formula on another step by noting that, as we saw in clip 2, the probability of a discrete random variable taking a specific value is simply the probability distribution function evaluated at that value. For example, the probability of the signal x taking the value 2 in the slide is the value of fx at x equals 2. We can therefore simply take our formula for the mean in terms of probability p and substitute in the distribution function f to get the final result that the mean or expected value of a random variable x can be found by summing the product of the variable times its distribution function over its range. Things are a little more complicated for a continuous process because the probability of the variable taking a value in a specific range is the integral or area under the distribution function over that range. And when we substitute this probability into the mean equation, the final formula also involves integration. Now we could evaluate sums like this using tables or the numerical method we used in clip 2, but in general we don't really want to get into these fairly tricksy integral equations, and so wherever possible we'll use the coarser but much more convenient measures of mean and variance. Let's return to the probability distribution for the discrete student height example and apply our new formula for the mean, where the values of x run from 61 to 73 inches, and the corresponding values of f are 0.05, 0.18, 0.42, 0.27 and 0.08, giving the result as a mean height of 67.45 inches. We can, however, also find the average directly from the signal. That is, the individual student heights of 5 students at height 61, plus 18 at 64, plus 42 at 67, plus 27 at 70 and 8 at 73, divided by the total number of 100 students. It's worth noting here that these formulae for the expectation or mean of a random variable in terms of the probability distribution also work for other statistics or functions of x, say g of x, by replacing the variable x with the function g of x. And in particular, if we're interested in the square of the signal, as we might just well be, we can just replace x in our original formula by x squared to find the mean square value instead of the mean. And now we have all the ammunition we need to look at variance. To measure signal strength, we need to take an average of some kind, but taking a simple average is no good, as the positive and negative going peaks in the signal will cancel each other out. The standard trick in this situation is to square the signal, so that all values head in the same direction, and can now be melted down to find an average. This is the mean square value of the signal. However, I've cheated here a bit by considering a zero mean signal. We really need to take a measure of how far the signal spreads around the mean. In fact, there are a number of measures or moments about the mean we could take. The first moment isn't much good, as the average distance of the signal from the average is 0, else it wouldn't be the average. The second moment, or variance, however, is the one we want. It measures the mean square of the signal distance from the mean. We can calculate it using our probability distribution formula with the square of x minus the mean, replacing x. The third moment, incidentally, is also useful as it indicates an asymmetry in the distribution, but we'll stick with the variance at this point. This is the variance calculation for our example, along with the MATLAB code. For each value of x from 61 to 73, we subtract the mean and square the result, and then sum the product times the function value of the range of x. We can write the variance in terms of expectations like this, since the expectation is simply the mean, and we can replace the average value straight line hats by expectations. If our signals aren't 0, as here, we can still find the variance using this formula, which works because the average of the average is still the average. It states that the variance of a non-zero mean process is the mean value of the square of the signal minus the square of the mean of the signal. However, we can avoid this complication by considering zero mean signals only wherever possible, when the variance is simply defined as the mean value of the square of the signal. So to summarize, variance is the average value of the square of the signal amplitude from the mean. For zero mean signals, it's simply the average value of the square of the signal, and we can calculate it either directly from the signal itself or by using our distribution function formula. And since the Gaussian distribution has only two parameters, the mean and standard deviation sigma, we will now mostly ignore the mean and just use the variance or square of the standard deviation as our measure of the amplitude of the noise signal. This slide shows Gaussian distributions with variances of 1/4, 1 and 4, recalling that the area under probability distributions is 1. The larger the variance, the greater the signal values of x which are contained. And these are the corresponding signals. Owing to the square in the definition of variance, the amplitudes go up according to the square roots, so here an increase of variance by 4 doubles the average signal intensity. Now we can calculate signal intensity or variance either directly from the distribution or from signal samples. But it's often useful to be able to get a quick estimate for the mean and variance of a signal by just gazing at it. There are gotchas here, but we can use the probability rules for Gaussian distributions to do this. The mean is simply midway between the highest and lowest signal values, and the variance is the square of the standard deviation. And with this captured signal, the mean estimate comes out as 5.5, and the variance as 12.3. These values are ballpark, mainly owing to the Gaussian tendency for large occasional spikes. Well, having looked at amplitude measures of stochastic signals, we can progress in the next clip to look at time and frequency response measures.